All right, so what I am going to talk about is a recent result which has a fairly long title, and it's the impossibility of low rank representations of, well, I'm just going to put this in quotes and I'll explain this later, of social networks. And so this is recent work. This is joint work with it's myself, it's Anish Sharma, who's at Google now, our own Andrew Stolman, and Ashish Goyal at Stanford. And so this was a paper that basically it's pretty much, it appeared this month, and it's in the Proceedings of the National Academy of Sciences in 2020. So before I get into the details of the results and what's going on, let me first tell you what low rank representations mean. So the idea is, you start with your graph, a social network, right? So you have your social network here, which I will describe just as a graph. And think of it as, for now, it's a simple undirected graph. And you want to do some ML tasks on G. So what are the kinds of tasks you may want to do? So for example, you may want to do link prediction. So link prediction means you'd like to determine which of these edges are likely to form in the future. You may want to perform community detection. And so typically what one thinks is that this social network contains a bunch of different communities and edges going between these communities, and you'd like to determine which of these vertices are in the same community, and the list goes on. There could be lots of different tasks that you would like to do. Now, a social network is fundamentally a discrete object, right? It's defined, you can think of it as basically defined by an adjacency matrix, which you can of course store instead as an adjacency list. And this representation might be somewhat inconvenient for machine learning. Firstly, it's extremely large. If you were to think of the raw representation of the adjacency matrix, this is like n squared, right? So it's like, so let's just say V is n, and the number of edges is m, and you think of m as O of n. It's a sparse graph. So what low rank, or I should actually have said low dimensional representations does is it sort of allows us to compress this graph in some form, which is now convenient for machine learning. So any questions? Is everything clear over here? Hopefully you can all hear me and I'm not speaking in the empty space.
Yes.
Yep. All right. So what low dimensional representations are going to do, so let me zoom out a bit. What low dimensional representations are going to do is it's going to start with the graph. Technically, it's going to map every vertex in V to a vector. And I'm going to somewhat abuse notation and just use the same V for vertex and vector in R to the V. So you're going to start with your graph, So here's your G. And you want to transform this into a collection of vectors where each vertex gets mapped to a vector. So you can think of, instead of your n cross n adjacency matrix, you have now represented this as n d-dimensional vectors. Right? So the representation goes from n times n to n times d. So you'd like to convert this graph into a collection of vectors, and this should be small. And then what you can do is feed these vectors into your machine learning model for link prediction, community detection, so on and so forth. And typically the idea is that, you know, edges over here, so let me just move my book a little bit. Edges should essentially be similar to proximity in R to the D, and typically one measures proximity by dot product. So this is what you want to do, and this is the low dimensional or the low rank representation. So a matrix view, to think of this as, here is your n cross n matrix, and you have now converted them into an d cross n or n cross d. So I'm just going to think of all of these vectors as column vectors for convenience. Okay, so my graph over here, which is represented in the adjacency matrix, gets converted into this matrix over here. Okay, and this matrix, let me, again, somewhat abusing notation, and there's sort of a reason to abuse this notation. Well, okay, no, let me just refer to this matrix as. Okay, so does this, any questions about this? This is essentially the process of low rank representation.
So when we are saying low rank, should we think of D as like log n or something, or like what is low?
Good question. So what should you think of D? Asymptotically, you would like to think of it as log n. In practice, you know, so because it's hard to associate a specific asymptote to a number, you should think of typically n will be in the order of millions, and D will be like maybe 100, at most 1,000. Typically, the experiments one does are when D is 100.
Okay.
Yeah. Okay. So, by the way, I mean, yeah. Okay. So. Okay, so now that now you know we've discussed this, so let me now give you a specific example of this. And a simple way to get a low dimensional representation is just SVD, right? So what would SVD do? So in SVD, you would start with the graph. You can just start with it as an adjacency matrix, right? And you know, let's keep things simple for now. So let's just say this is, you know, this is symmetric. Just to keep things simple. And what is SVD going to do? So think of these as your vertices, right? So these are your vectors. And you want to sort of compress these vectors. So what SVD would do is it essentially factorizes this matrix, right? So it'll say that this matrix is approximately, and again, specifically here, I'm doing SVD for the symmetric case, which is essentially the eigenvalue decomposition, where you would say that, let me write this out sort of in the following form, which is this, these are your d-dimensional vectors. Okay, so this is the matrix M. And let me now multiply it by M transpose, right? So this is going to be D times N. So SVD says, I'm going to take your matrix and I'm going to factorize it into a product. Essentially, it becomes a Gramian matrix. A Gram matrix is simply all dot products amongst a set of vectors. So in other words, this is just saying that in this matrix, the ijth entry is going to be approximately, so if I look at I over here and J over here, and remember, I map I to this vector V of I, or I guess I'm mixing up my I and J. I should have maybe called this I and this is J. So I'm saying the ijth entry is approximately equal to Vi dot Vj. And that's effectively what SVD does. SVD says, given a matrix, I'm going to try to find some small d such that this is true. This equality is approximately true. And indeed, this small d can be found by looking at the singular vectors and the singular value decomposition of the matrix. So instead of, I'm jumping, I'm saying SVD to a low rank matrix factorization. So to be more precise, I should have said SVD is not this process. SVD is a specific method to achieve some kind of approximation of this form. Now, one can think of many other different ways of trying to factorize your matrix in this way. But in effect, no matter what method you're doing, what you have is some correspondence between the ijth entry and some function of the dot product. Maybe it's not just identity, it's typically some other function of the dot product of the matrix, which means that this is sort of saying similarity, and this is saying there's an edge. So an edge corresponds to similarity. And that's in some sense the philosophy between all of these low rank matrix factorizations and the use of SVD, or now you can use some other method to do this. And so, but this is a method that converts your vectors into, converts your graph into a collection of vectors. So SVD is of course one such method, but there are many others. There's deep walk, there's node to vec, there's something called line, and there are a bunch of other fairly famous, highly cited results that perform such a process for a graph. And some of these methods use neural nets, some of these methods use some optimization, but in the end, the philosophy is something like this, where maybe instead of you have approximately equal to the dot product, it's equal to some function of the dot product. Okay, so is this, does this make sense?
And just one.
Yes.
One question.
Yes.
So I assume the adjacent matrix, the entries are 0 or 1, right?
Yes.
So is that, we don't really need to approximate the 0, 1 value.
Fine. So yeah, so let me now, that's a good point. So let me now define this somewhat more. You're right that this is a Boolean matrix and this is not Boolean. So what you can do is typically interpret this as a probability.
Okay.
Say that is the probability of that entry.
Okay.
Yeah.
Okay.
Good point.
Thanks.
Yeah. All right. So now what I'm going to do is, given this question, let me think of this same process in a different way, which is let me think of it as a graph model instead. So that is, instead of thinking of my graphs as the input and me trying to find these vectors according to an optimization, I can have a different perspective, which is a statistical model of how a social network is created. So my model is going to posit that every vertex V is really a vector in R to B, and that's what I call the vector B. And I also think of D as small. And then I'm going, so now I'm actually defining a graph model. I'm going to say that, then I'll say, okay, so let me sort of update my notation and let me write it in the following way. So every vertex I is really a vector that I'll call VI. And I'll say edge ij forms with probability vi dot vj. Now, this is a bit of a fudge because this number, it might not even be positive. It might not be positive. It might be more than one. So let me instead say that I'm going to take the min of this dot product. But I'll also take a max with that. Just to give you a pictorial view, I'm just saying that here is vi dot vj. Here is the probability of an edge. And I'm saying that if the dot product is negative, the probability is 0. Between 0 and 1, it's just equal, and otherwise it's 1. So if the dot product is more than 1, I'm going to say they're going to be connected. So this gives me a model.
And so we're not normalizing the vectors in any way?
We are not normalizing the vectors, but you could also, yeah, you could, this actually subsumes the normalization case, right? Because you could then pre-normalize everything and use this model. And another interpretation to low rank representations, which would be more of maybe a Bayesian view, is now I can say given G, determine the VIs most likely to generate G, right? So now you think of it as parameter fitting. So you fit these parameters to match the observation that you got. And you want to find these vectors, right? So you want to find, in some sense, in this case, these would be like the parameters of your model. So you fit the model and then you maximize, you get a maximum likelihood estimate. And then, you can think of using different norms and what have you. But overall, the idea is you're using the dot product as some measure of similarity. Okay, so is that...
So when you say most likely to generate G, does that mean to generate G specifically, like the probability of generating G, or in some way taking into account generating something that is close to G?
So essentially, you can fold these together. It's usually generating G specifically, but if you think about it, okay, I should have put something forms, I'll say independently with probability, right? So then all of these probabilities will factor out into a product of these. So you could think of, you're trying to sort of maximize the most number of edges, or probably some kind of like symmetric difference, like weighted by all of these things. Does that make sense?
Yeah.
I mean, essentially for any graph, so for any set of vectors and any graph, there is a probability that that graph is generated by these vectors. So you could then try to optimize that function, which is the probability function. Okay. All right. So, so I'm giving you these two different views of what a low rank representation is, just to tell you that, to show you that it's a very reasonable way of thinking about graphs. And if you ask what these dimensions are, often people will say these dimensions are basically like our fundamental axes of interest. So maybe these dimensions represent, politics, sports, the college that you went to, whatever have you. These are the few dimensions that effectively determine whether we are connected or not. And so what you can say is, given the graph, even though you don't know what these dimensions are, a procedure like SVD or these other matrix factorization methods will essentially find these from the data itself. And so this is a very appealing view, especially in machine learning, that you have the data, all you have is connectivity information, so you have the graph, but you're able to discover the relevant dimensions of interest. So far, so good? Okay. So now let me continue, and now let me tell you about our result. And our result, in some sense, goes contrary to this theme. The main message that I'm going to say is that low-dimensional representations, or I'll say embeddings. So I'll now refer to these as low-dimensional embeddings. Okay, I'm going to make a statement which maybe is more than what I can show, but then let me try to justify why I'm making the statement. I'll say, provably, cannot capture the social structure of real social networks. So I'm making a bold statement here. So technically I should say some low-dimensional representations. I cannot do this, I cannot prove this for all, but I can do it for one that is fairly commonly used. And what is surprising about here is really that what all of this work suggests is that real-world social networks, they are fundamentally high-dimensional. So I want to emphasize that this is somewhat of a contrarian view, given sort of a lot of contemporary machine learning on graphs, where there's a lot of work that goes into optimizing and finding various good low-dimensional representations, and a lot of validation done on real data. And you might say, well, how can you then argue that it provably does not capture the structure? There seems to be some disconnect here. And honestly, I don't have a good answer. I think part of it may be that there are some artifacts in these methods that are actually discovering some structure, but our experiments also show that it doesn't do as well as one might think. So now, so there are two aspects here, right? How does one make a provable statement? Because a lot of these, so this I was able to define. A low-dimensional representation is something that I can define formally. But what does it mean to say social structure of real social networks? So now let me get into the definitions. Okay. So I need a proxy to measure social structure, and the proxy that I'm going to use are triangles. So what I mean is, if you take your average social network, you will have lots of triangles. Friends of friends are often friends. Moreover, so social networks have lots of triangles. They're also sparse. And this is something I alluded to earlier, that M is O of N. The average degree is constant. And usually the vast majority of vertices have low degree. Now I'll give you examples where I kind of quantify this, but one way to think of this is that N, think of it as, let's say that N is like 1,000,000. Whereas the average degree is typically something like 10 to 100. And most vertices, by vast majority, you could imagine that about 90% of your vertices have a degree of, let's say, at most 20. I'm just putting some numbers over here so that you get a feel. And we'll see some examples where we'll actually quantify. I can give you concrete examples. So typical social networks, and this is something that is pretty much it's uncontroversial and it's fairly unambiguous, that most people will agree that the graphs are sparse because you can run these measurements. They have lots of triangles, but moreover, lots of triangles incident to low degree vertices. Okay, so let me sort of quantify this. So let me say that for a degree, and let me use okay, so let me use D for a degree. So this is not the for a degree D. Let delta of D be the number of triangles that only involve vertices of degree at most D. Okay, does this make sense? So I start with my graph. I look at all the vertices whose degree is at most D. So that's some subset of vertices. So these are all the vertices where the degree is at most D. And then I count how many triangles there are in here. And that is delta D. So while we know that the number of triangles in social networks is large, you could ask, but are these triangles coming from high degree vertices or low degree vertices? And actually it turns out they're coming from, many of the triangles are coming from low degree vertices, not all, but many. So the sort of claim I'm making, and I'll say this sort of in real social networks, for D being O of 1, so D is constant, D being O of 1, delta D is actually omega of n, meaning that even when you look at low degree vertices, the number of triangles is actually quite large. So another way to think of this is that when D is O of 1, that means I'm looking at only the portion of the graph with constant degree. It can have at most n triangles, or at most O of n triangles, and it actually has omega of n triangles. It actually has at least some factor of n triangles. Does this make sense? And I claim that this is some kind of proxy. It's a measurable proxy for social structure. So what I'm claiming, so let me just let me get this out of the way. I'm saying that this is some kind of proxy for the social structure of the graph. So at this point, I want to pause and make sure that what I said makes sense. So please ask me questions if this makes sense. So I'm claiming that in real social networks, if you look at the vertices of degree at most, let's say twice the average degree, some constant, and we'll worry about quantifying these exactly, but asymptotically, when the degree is constant, the number of triangles incident to only low degree vertices is still omega of n. Questions?
And so you're saying that with whatever low dimensional embedding method you're looking at, this doesn't hold in the low dimensional version?
I will get to that. So what I want to say is that this is a measurable property, and in social networks, this holds. And this is a common proxy for social structure in the sense that we believe that triangles are a fundamental manifestation of the social structure. And the fact that there are many triangles incident to low degree vertices is again, some specific manifestation of the social structure. And now, in some sense, the main result the main result is that a low-dimensional embedding using the what I'll call truncated dot product function. And again, like I'll come back to this later, but this was this function that said max of 0, min of vi dot bj comma 1. Like this is what I call the truncated dot product. You take the so a low-dimensional embedding that uses the truncated dot product cannot, and what I mean with cannot is really with extremely, well, let me quantify this shortly. I'll say cannot generate graphs where delta D is omega of n for D being O of 1. So a low-dimensional embedding using the truncated dot product function cannot generate graphs where this holds. So if you think that this is an important aspect of social structure, then I'm claiming that a low-dimensional embedding that uses, of course, this specific dot product function cannot generate these graphs. And this is, again, with cannot, it's basically, it generates it with extremely low probability. It cannot generate graphs, and I'll say this is to qualify this, I'll say with any reasonable probability. Any reasonable probability. Again, you can ask me later about quantifying this explicitly. That's not as important. What is important is really that when you use the dot product and use a low-dimensional embedding, you actually cannot generate these graphs. Indeed, we prove that the dimension required is essentially n over log n. So it's not, it's really bad. It basically says that you need roughly linear dimension, which now goes against the general sort of perception or the belief that one can have low dimensional embeddings that capture social structure. Again, the result does not rule out other possible functions, although our empirical results, do seem to suggest that this impossibility will also hold for other functions. But mathematically, and what is interesting here is that any low-dimensional embedding, I'm not using SVD. I'm just saying you give me any method you want to factorize. So you might do something with neural nets, you might do something with any other optimization. Fundamentally, low-dimensional space does not have enough, apologies for the pun, but doesn't have enough space to generate enough triangles. Okay, and now I think just before I maybe touch upon the math, let me sort of show you specifically what I mean using showing you some of the plots, showing just a couple of plots from the paper. But any questions at this point?
So if D increases from constant, is there like a relation of what is the dimension required? Like, for example, if D is log n or it grows slightly bigger than log n.
Oh, no, so this is, yeah, that's a good question. So actually it's quite robust. So the dimension required is n divided by log n times poly D.
Okay.
So I actually think that the poly D is just, it's a weakness of the analysis, probably n divided by D log n.
Okay.
So it's very robust to that. It's, I see what you mean. If it was n divided by 2 to the D log n, then you say, well, it's not that bad, but it's actually n divided by poly D. And all there are all these constants that are sort of here and here, and the dependencies are all polynomial on those constants.
Okay. Okay.
So now let me just, let me show you a specific picture so that some of this becomes concrete. So I'm just going to sort of stop the sharing for now. And let me just pull up, sorry, give me 1 second. here. And let me now share the screen here. So hopefully all of you can see what's over here. You can see the paper.
Yes.
Okay. And so I'm just going to show you an example result over here. Okay, so let me bring back some of the specifics that I said here. So remember that over here, I defined this delta D, right? So in this plot over here, the delta is normalized by n. That is sort of unimportant. What you see on the x-axis here, okay, so there is a specific, in this case, it's a co-authorship network, a different kind of social network. The x-axis is the degree. The y-axis is basically this value of delta, except I divided by n, divided by the total number of vertices. So what you can see is that even when I look at a degree of 10, the total number of triangles is like n divided by 10. So there are, and n in this case is I think about maybe 10,000 or 10, I believe it's about 10 or 20,000. And so even when you look at vertices of degree at most 10, they involve something like, you know, n divided by 10 vertices. So a lot of triangles. They involve a lot of triangles. So this is the plot of C versus delta of C. So I should have used C over here, but I said for degree D. So you could plot delta D versus D. That's what's being plotted here. This is delta D and this is D. And you can see, so this is basically the minimum degree. So it starts there and it goes like that. These are the corresponding plots essentially of graphs generated by a number of different embedding schemes, low dimensional embedding schemes. And this involves things beyond the truncated dot product. So this involves, in this case, there are 7 different methods that we use. And some of them are based on SVD, some of them are based on Note-to-Vec. They use different functions of the dot product. But what you can see consistently amongst all of these is that there is a huge gap over here. They are not able to capture the triangles incident to low degree vertices consistently for all of these methods. And this is also consistent with many different graphs that we tried on. So this is in some sense the main message, this gap over here. And this is worrisome because one believes that this accounts for a lot of social structure. Remember, the number of vertices of degree at most 10 or 20 account for the vast majority of vertices in your social network. So this is, you know, most of the vertices are here, and the subgraph on most of the vertices involve lots of triangles, and yet these methods are unable to get them. Our mathematics only works for the truncated dot product, but empirically it seems to be consistent for other methods as well. So are there any questions about that?
But so you say that there are lots of machine learning methods on that use low dimensional embeddings?
Yes.
And like, so if this property is important, why do those work?
So I guess the question is, what does it mean to work? Right, so it could be that, you know, these are being done on downstream applications where maybe one, so what is happening is that a lot of the embedding methods are being compared to other embedding methods. So the fact that they work means they work better than maybe SVD.
Okay.
You know, there has been other empirical work, you know, coming out of Ohio State that suggests that for many of these machine learning tasks, there are existing methods that beat embeddings. Part of it is also, it also depends on how you define your experiment. So when you do link prediction, the typical mechanism to do link prediction is, you know, so let me sort of draw this over here. You know, let's say you start with a graph and you want to do link prediction. You want to run a link prediction experiment. What you'll do is you'll take some portion of the graph, you'll delete a bunch of edges, right? So now you construct G prime, which is this graph over here without those edges. And then you will say, can I predict that these edges existed? Now, if it turns out that you deleted all your edges from a large, dense component of your graph, then it is possible that maybe one of these methods would work. But if you deleted edges from sort of spread across the entire graph, then you might not be able to recover. So I think a lot of the devil is in the details of how these experiments are done and how things are justified.
If I can also say something about that, I think part of it is that the way that they're reporting that it works, they're using these regular like machine learning metrics saying like, oh, we predicted the right answer 75% of the time or something. And the plots we've got here with these triangle densities is a more subtle thing. Like it could still be guessing right 90% of the time and messing up on all the triangles.
Yeah, it's another good point. So I think that, it's because these are measured with very coarse, like precision recall measures, where it could be that essentially, you're dealing with a portion of the graph that's sort of easy to deal with anyway. But I think that this is a very valid question, is really how do you square, these results with the supposed successes of these methods? And I think that is, it's a very interesting future work to be done. Okay, so since I have, I don't have much time left, I have about 10 minutes. What I want to do is now I want to give you sort of some hint about how to prove this. And so what I'll do is, okay. Can everyone still see my screen? Yeah?
Yeah.
Okay, all right. So now let me tell you about how one proves this. And I think this is actually sort of very interesting. So I'm going to just sort of walk through the proof in, somewhat of a haphazard, somewhat of a stream of consciousness-ish way to demonstrate sort of the main tools that are used. So I started with my vectors v1 up to vn. And I'm going to, remember, so these are vectors in R to the D. Okay, so let me now represent this matrix. This is what I called, this is M, right? And so these are the column vectors. Now let me take M transpose here. So I look at M transpose M. So that gives me an N cross N matrix. And then I'm going to apply the sort of truncation function to each of these. Right, I'm going to sort of truncate them by 1 and 0. I'm going to do this min and max procedure to get another matrix. Right, this is the truncated matrix. And now all the entries over here, all the entries are in 0 and 1. So they can be interpreted as probabilities. So now I started with my vectors. I took the gram matrix. I truncated the entries so that now all the entries in here are between 0 and 1. And now I can use this to construct a graph, because I can basically pick the edge ij is chosen with a probability pij, where pij is exactly this entry, right? So this is the process. I started with my vectors, I looked at the gram matrix, I truncated the gram matrix, and I go and generate the graph. And I want to study the properties of this graph over here. I'm going to make two simplifying assumptions. And let's assume that the VIs are all non-negative. Okay. And let me also assume that all the lengths are exactly the same. This is a simplifying assumption, and we can prove it, without this assumption. But when you make this assumption, the math becomes simpler. What is interesting is now the dimension required actually becomes n, not just n over log n. So if all the vectors have the same length, then the lower bound is even stronger. So what I'm going to show you.
You're saying the length was the important part there?
Yes, the fact that the lengths are different was important. Not that there is I'm just assuming that all the lengths are the same. And when the lengths are the same, the dimension is actually omega n.
But like restricting that they were positive didn't matter?
Restricting they were positive doesn't matter. Although it requires a lot of, you know, more sort of painful math to deal with the negative case, but the lower bound actually went through. Okay, so let's try to understand. I want to give you some sort of geometric intuition as to, you know, what's going on here. So here's the picture that I have in mind. Okay, so these are your vectors, right? So on and so forth. Okay. Now, your graph has lots of triangles. Let's just focus on vertices of low degree. So let's just say all of these vertices of low degree. So there are lots of triangles here. Okay. Now let's look at how you would generate a triangle. You have to generate this edge here, this edge here, and this edge here. You have to generate these three edges, and all of them are being generated independently. So you have to independently generate these three edges. What does that mean? It means you need to pack these vectors close to each other, right? So when you've got a cluster of vectors that are close to each other, they will generate a triangle. Except, what does close really mean over here? So let's just say you want to, let's take a simple example. Let's say you want to generate this triangle. So you need these three vectors to be close to each other. You want to generate, you want to generate this triangle, which is disjoint from this. So this triangle comes from there. This triangle, maybe it comes from these three. So you want these three to be close to each other. And you have another triangle here. And so you have this. Now, as you put more and more triangles, remember, there are going to be something like n such triangles that are even disjoint. I mean, you can sort of argue that essentially there are going to be omega n such disjoint triangles that you need to put. Except you only have d dimensions, and if d is much, much smaller than n, what's going to happen is that at some point, the angle between this vector and this vector, this cannot be orthogonal too long. Like as you put more and more triangles, because your dimension is much smaller than the number of triangles you want to put, at some point the angle between these vectors is going to start becoming small. Now the moment the angle becomes small, you might now start forming this edge. So as you pack more and more triangles, the problem is you'll start forming too many edges across these triangles, and then the average degree goes up. So now here's the tension that you have. You need to place, so think of it, you need to place n triangles, and I'll even say disjoint triangles, right? In, we'll just say r plus to the d, but the overall graph must be sparse. Now, intuitively, if you put n vectors in d-dimensional space, the average dot product between them, I mean, the average angle between them, so like, you know, you've got d-dimensional space here, right? So d is small, and you put many vectors. If you put many vectors, there cannot be too many pairs that are going to be orthogonal. So basically what happens is now too many edges start forming. And so this in some sense is the tension that you have. So another way to sort of think about this is one way to prevent a lot of these edges from being forming is to make the vectors smaller and smaller. Because when you make the vectors smaller, the dot product goes down. But when you make the vectors smaller, the probability of the triangle forming goes down. So this is the tension. To make triangles, you need the vectors to be long. But because you have lots of triangles, these long vectors are going to have non-trivial dot products amongst each other and then form too many edges. This is sort of the geometric picture that you then have to sort of mathematically make form. And we use sort of some tools essentially some tools about, sort of various matrix norms to sort of pull this off. So at this point, I'm out of time. So it's 2:58. I think I've given you sort of the basic result, some sort of, wishy-washy, hand-wavy geometric picture of why something like this would be true. But, I'll sort of leave the specifics of the math to questions. Okay, so I'll end here. And, but, if you have any questions, shoot.
So do you finally prove like either the graph will be sparse or the graph will be having a lot of triangles on low degree vertices?
The opposite is, well, essentially what we prove is if the graph has lots of triangles on low degree vertices, then the graph becomes dense.
I see.
But then if the graph is dense, then, you have a contradiction, right? Because you started off with many triangles incident to low degree vertices.
So are these two assumptions kind of the full characteristics of social network, that sparsity and?
That's a good question. I mean, I don't think they completely characterize. And I think this, in some sense, this is this problem that people have, done for a really long time, which is how do you characterize social networks? And I'm sort of wary of going down that path because there is no model which everybody believes. Instead, there are certain graph theoretic properties that when you measure them are fairly consistent. And I think that those are really so I prefer to focus on those quantities. And, sparsity and lots of triangles is something that is sort of uncontroversially something that everyone accepts.
Okay.